We'll continue our discussion on heuristics for pairwise sequence alignment. Today we are specifically going to look at the concept of maximal unique matches. So just to do a quick recap from the last lecture. In the last lecture we saw motivation for why we need heuristics for sequence alignment. We saw the example from Genome India project where the data is so big and we cannot use the exact dynamic programming methods that we have been using or discussing so far. We also saw how heuristics work, like we saw roughly what is the intuition that we follow, and there we discussed that the basic intuition that is being followed is that the exact pattern matching solutions are significantly faster compared to the sequence alignment algorithms that we have seen. So we have been using this exact pattern matching as a guidance for locating the regions in the large text where the pattern may align. So because this exact pattern matching can be done much faster, we are using this as a proxy to guide us where the alignments may occur. Now one technique that we looked for computing exact matches in the last lecture was using this minimizer technique, where we said that one way of going about computing exact matches would be to look for all matches of k length words between two sequences, and a slightly smarter way could be to use minimizer technique to sample k-mers and then compute k-mer matches, and we saw some interesting properties that come from this minimizer technique. Now for today we are going to look at another technique for computing exact matches, which is known as maximal unique matches. Now one key difference between these two techniques will be that in the minimizer or k-mer based methods, the length of the exact matches was constant. So depending on the parameter k, the length of the exact matches that we were computing were of constant lengths, whereas now we will allow these matches to have variable lengths, and we will define this properly in the next few slides. So again a quick recap. So the basis for using heuristics has been that we have discussed this dynamic programming methods. So for eddy distance, global alignment, all these problem versions require order mn time, where m is the length of first sequence and n is the length of second sequence, and using these algorithms at scale is not feasible. So that is why, using the fact that exact pattern matching can be solved quickly, we are discussing heuristics where we can solve exact pattern matching problem first. Now in all these heuristics for pairwise sequence alignments, the key idea is to avoid computing the entire dynamic programming table. So if you notice all the alignment methods that we have discussed, they all require computing this large dynamic programming table using different types of recursions, but the key thing that we want to do in heuristics is to avoid computing this entire table, and for that the basic intuition that we are following is that we can use and we can compute short exact matches between the pattern and the text, and then we can consider only those regions in the text where we see sufficient number of these exact matches. So as a intuitive idea is to look for those regions in the text where we see a good enough cluster of these exact matches, and subsequently we can focus our dynamic programming recursion in only those regions where we think that those are the promising regions in the text. The hope is that such dynamic programming will give us the optimal alignment in practice. So in the last lecture we discussed minimizer technique for computing exact matches. We will continue our discussion of computing exact matches between text and pattern, and so we will look at another technique today, which is known as maximal unique matches. So as I said, maximal unique matches differ from k-mer matches because they can be of variable length. So now there is no fixed length of a match, they are allowed to be of variable length. So let us discuss some definitions. So first is a trivial definition of an exact match. Well, exact match is simply when we are given two strings A and B, let us say of length m and n, then exact match is nothing but a substring occurring in both strings, right. So for example, if the common substring occurs at position P1 in A and let us say position P2 in B, so this should be position P2 in sequence B, then we know that there is a substring match between both sequences. So if the substring is of length L, then a short way of showing this notation is L comma P1 comma P2, indicating that there is a exact match of length L at position P1 of sequence A and position P2 of sequence B. Now there can be many exact matches between both strings and all of them can be denoted as these tuples. Now next definition that I want to give is maximal exact match. A maximal exact so an exact match L P1 P2 is maximal if it cannot be extended towards the left as well as towards the right. What do I mean by that? Well, if we look at the immediate left character of this match in the sequence A, then that differs from the immediate left character on sequence B. That is, if I extend my match further towards one character, then I will see a mismatch and I will not be able to extend the match further. So this is also known as left maximality. Similarly, for right maximality, I can say that the immediate right character after the match, that is A P1 plus Lth character of sequence A, has a mismatch with P1, so this should be P2, so this should be P2 plus Lth character of B. So this is right maximality, that is to say that the right, I cannot grow my match towards the right of the sequence. So in a way that this match is maximal on both sides. So to see an example, so consider this sequence match AT. So the substring AT is common in both sequences, so therefore AT is a match, right. However, is it maximal? Well, in this case it is not maximal, because you can see that I can extend this match right by one position. So here C and C characters are matching. So this match can further be extended towards right by one letter. So therefore AT is not a maximal match. What about CCA? Well, if you look at the left character, they both are mismatching, and if you look at the right characters, they both are mismatching again. So this time, this particular exact match is can be said as a maximal exact match, because we cannot extend it on left and right directions. Now in this definition, I am omitting a corner case. What happens if my string is on the boundary of the sequence? So for example, in this case there is a exact match of substring ATCG, but however notice that there is no right character here. In this case also we can say that this match is right maximal, because we cannot extend it further by one letter on the right side. In fact, we cannot also extend this on the left side, because A and C are mismatching. As a result, ATCG is a maximal exact match in this example. Similarly, again this G is a maximal exact match as well, because you cannot extend it towards the left as well as you cannot extend it towards the right. So, I hope by this the definition of maximal exact match is clear. So, just to make this correction, this should be P2 and this should be at position P2 in B. Okay. Now, maximal exact matches can also be used as exact matches when we are comparing two large genomes. But it turns out that when we are comparing large genomes which are similar, for example, let us say human versus chimpanzee or human versus mouse, then it turns out that sometimes the number of maximal exact matches can be very large. In fact, sometimes it can be very large to deal with in the downstream steps. For example, in the later steps when we want to cluster these matches and when we want to solve dynamic programming, the number of exact matches can be too large to handle. So, for example, in the literature we find that what people have reported is that between human and chimpanzee genomes, the number of maximal matches is well over 100 million. As a result, because maximal exact matches can be too many, we look for one alternative definition of computing matches, and there that is what motivates the maximal unique match. Now, to control the number of matches, what we are going to put is another constraint, that is this uniqueness constraint. So, we want the matches to be maximal, but we also want them to be unique. And what do we mean by unique? Well, as before, we want the match to be left maximal, we want the match to be right maximal, however, we also want the substring to be unique, that is the corresponding substring should occur only once in string A and it should not occur elsewhere. So, for example, except position P1, it should not occur elsewhere in sequence A. Similarly, the same substring should not occur elsewhere except position P2 in sequence B. That is, the corresponding substring should have exactly one occurrence in sequence A and should have exactly one occurrence in sequence B. So, with this uniqueness constraint, what happens in practice is that the number of matches significantly reduces, and this in practice it turns out to be a reasonable method to compute exact matches and use them as a way to reduce the search space for alignments. So, let us look at some example. In the previous slide we saw that G is a maximal exact match because it is both left maximal and right maximal. But is this a maximal unique match as well? In this case it turns out no, because observe that this substring is not unique in the sequence A. So, for example, G occurs again at this position. So, therefore, it is not a unique substring of sequence A. As a result, it is not a maximal unique match. Even though it is a maximal exact match, it is not a maximal unique match, because for it is not satisfying the uniqueness property. Let us look at one more example, which is the ATCG example that we saw earlier. In this case, this is definitely a maximal exact match, but is it a maximal unique match? Well, as you can see, it is, because substring ATCG only occurs once in sequence A and it only occurs once in sequence B. Therefore, it is a maximal unique match. So, now with this definition So, wait, here is one more example. So, in this case CCA, well, this is definitely a maximal exact match because you cannot extend it left and right, and looks like this is also a maximal unique match because CCA occurs exactly once in sequence A as well as sequence B. So, this is a maximal unique match. Now, how do we compute all these maximal unique matches between two strings? Because our goal is to identify all maximal unique matches, so that we can identify the regions in the text where we should be aligning the pattern. Now, it is not a trivial problem because if you think about it, like maybe if we think of a brute force way, like maybe if I suppose I want to enumerate all possible string pairs. So, if I enumerate all possible substring pairs and I check one by one whether they satisfy all these properties or not, then it is going to be taking too much time, like this will be very slow. So, there are too many substring pairs to consider, and then checking for all these conditions will require additional time. So, brute force method is not going to work. What else can we do? Well, as we have seen in the module 2 of this course, we can use some interesting string data structures. So, we already saw suffix trees, suffix arrays and ideas like that. It turns out that this problem can be easily solved and it can be very efficiently solved using suffix trees. So, we have seen some examples for the problems where the problems look very complicated in the beginning, but with suffix trees we always come up with a very elegant and fast solution to solve those problems. And it turns out that for this problem as well, we can find an efficient solution using suffix tree data structure. Now, we have already discussed suffix tree data structure in module 2 of this course. So, I assume that you are familiar with the properties of suffix trees. So, just to frame the problem formally, we are given two strings S1 and S2 of length m and n respectively, and as output we want to report all maximal unique matches between these two strings. And as I said, like other problems discussed in the previous lectures, using suffix trees will give us a fast and simple solution to solve this problem. In fact, I encourage you to pause this video and try yourself to solve this problem in using suffix trees. Okay. So, let us look at how we can use suffix trees to solve this problem. The first step, as usual in problems like this, will be to build a generalized suffix tree. So, remember that in generalized suffix trees we concatenate the two strings, we separate them by delimiters and we concatenate two strings and we build a common suffix tree for the concatenated string. And we know that suffix trees can be constructed in linear time. So, therefore, suffix tree construction can be done efficiently in linear time only. So, for example, if I consider this example, then my generalized suffix tree is going to look like this. Now, we have to somehow use this suffix tree to compute all maximal unique matches. Now, remember that we are again going to use the fact that every substring of sequence 1 and every substring of sequence 2 will be a path from root onwards. So, if I consider any substring, it will be spelled by a path from root towards the bottom. So, every substring will be spelled as a path, because remember that suffix trees spell suffixes of S1 as well as S2. So, each path from root node to leaf node represents a suffix of either S1 or S2, and we cover all the suffixes. So, therefore, every substring can be located, or every substring of S1 can be spelled as some path from root node towards the leaf nodes. Okay. So, what next? Once we have built a suffix tree, what we are going to do next is we are going to label leaf nodes as either red color or in blue color, depending on whether the leaf node represents a suffix of the first string or the second string. So, if the leaf node represents a suffix of the first string, then we are going to label it as red. If it represents a suffix of second string, then we are going to label it as blue. And this is a trivial step, because all we have to do is just to traverse all the leaves of the tree and see where the suffix is coming from, and accordingly label the color. Now, as a next step, what we will do is we will do a bottom up traversal of the tree, and we will label the internal nodes as well. The policy that we will follow is that if the child nodes, if all the child nodes of a node have the same color, then we will label the node with that same color only. So, for example, if I have all my child nodes labeled as red color, then my internal node will also be labeled with a red color. And otherwise, if that is not the case, that is when your children have different colors, then I am going to label the node with purple. So, if my one node is red and other node is blue, then in that case I am going to label the parent node in purple. So, intuitively what you can see is what is happening is that we are just distinguishing whether the path labels, that is the path from root to that node. So, for any node the path, its path label, whether it is coming from first string or whether it is coming from second string or whether it belongs to both strings. So, for example, path label TG belongs to both strings because we have labeled it purple. So, the purple color indicates that the path label TG or the substring TG corresponds to both strings. So, it is shared by both strings S1 and S2. Whereas, if you see any path label that is corresponding to red colored node, then this path label will only occur in string 1, it will not be shared by string 2 and so on. So, these colors are telling us the origin of the path label, that is whether it is coming from string 1, string 2 or is it common to both. So, just to reiterate, so remember that the notation that we have been following is that the path label of a node V is the string spelled by the path from root node to V. So, if there is a node V and there is a root node, then the string spelled by the path from root node to V is called the path label of that node. Now, with this coloring mechanism, what we have achieved is that path label of each purple node will occur in both strings. Path label of each red node will occur in first string only, and path label of each blue node will occur in second string only, and that is because of the bottom up traversal that we have done. So, whenever we see that strings occur in both strings, we are coloring them with purple color, but if I see that all my children come from first string, then I know that my own path label will also belong to string 1 only. So, now this property can be very useful for computing maximal unique matches. What claim we can make here is that each maximal unique match must be the path label of a purple node that has exactly 2 leaf children, one red and one blue. That is, each maximal unique match must be the path label of the purple node that has exactly 2 leaf children, one red and one blue. So, what we are looking for, that each mum is a path label of a purple node that has exactly one red children, that is a leaf node, and one blue leaf node. So, this is a blue leaf node, and this is a red leaf node. Note that this is a one way property. We are not saying that this is not a if and only property. What all we are saying is that each mum must be a path label of a purple node that has exactly 2 leaf children, one red and one blue. And this is because of the properties that we have defined for maximal unique matches. Because maximal unique matches must be shared by both strings, and maximal unique match should occur only once in each string because of the uniqueness property. So, because it is shared, it would correspond to purple nodes, and because it occurs only once in each string, therefore, the purple node will have exactly one red children and one blue children leaf node, because it has only one occurrence in both strings. However, one caveat here is that this is just a one way property. What we can say, so one observation that we have to make here is that every purple node with exactly one red leaf child and one blue child may not be a mum. So, we know that this is a one way property. Every purple node that satisfies the property will not be a mum, and for that you can see this example as well. Because if you see this example, then observe that the path label of this purple node, which has exactly one red children and one blue children, this is not a maximal unique match, because if you see the occurrences of this substring, this is not maximal in the sense that you can extend it towards left by one position. So, you have a match of t characters on the left. So, I can extend it towards left by one position. So, therefore, this is not a maximal unique match, and as a result we have to be careful in selecting which purple nodes are corresponding to maximal unique matches. Now, it turns out that checking for left maximality is trivial, right. So, all we need to do is check the left character of each leaf node. So, for example, if I want to quickly check whether this is left maximal or not, I can check what is the suffix corresponding to this node. From the suffix I know that the starting position in the text, so where the suffix starts in the text, and I just need to look at the one left character of that suffix. So, for example, this particular suffix corresponds to this suffix in this string 1, and because I know the starting position of this suffix by the suffix id, I can quickly check what is the left character and save it here. Similarly, I can check the left character of this leaf node as well. So, this is $2 suffix. We know that this suffix starts here. I can move one character left in the text and recover the first left character, and I can save the left character here, that is what is the immediate left character before this suffix. And because I can compute these left characters, I can easily check whether this path label is left maximal or not. And in this case, because both leaf nodes have equal left characters, this is not left maximal, because it implies that I can extend my match left by one position as well. So, to summarize, all we have to do is to build a suffix tree of So, to build suffix tree of S1 $1 S2 $2, then for each leaf node in the tree we are going to compute the left character that occurs just before the suffix of that node. So, that were shown here. So, the left characters occurring before the suffixes, we will compute those for all leaf nodes, and then once we have computed the left characters of all the leaf nodes, we are going to locate all the internal nodes that satisfy all these properties. First, the internal node should have exactly 2 child leaves V1 and V2. One child must be a suffix from S1 and other must be a suffix from S2. That is, one should be a red leaf node and one should be a blue leaf node. And we have to check for left maximality, that is, the left character of V1 should be different from left character of V2. So, in this case this property is being satisfied, that is, the left characters are different. Therefore, this path label, that is TG, is actually a maximal unique match. So, TG is a maximal unique match, and you can see and verify from this example as well that TG is both right maximal, left maximal, and it occurs only once in S1, TG occurs only once in S2. So, therefore, TG is a maximal unique match, and all these operations can be done in linear time, because all we are doing is parsing the leaf nodes and then using any traversal of the tree we can check for these properties and compute the entire set of maximal unique matches in order m plus n time, that is, the length of both sequences time. So, this gives you a very fast way of solving for maximal unique matches. It also serves as another example for how suffix trees can enable a simple solution to a non-trivial problem. Now, what we can do now is that because we have an efficient algorithm to compute maximal unique matches, we can use them as exact matches in practice for alignment problems, and later on we can see how we can use these exact matches to solve approximate alignments as well. So, for example, these maximal unique matches are used in practice. So, as I mentioned in the last lecture as well, that these heuristics are commonly used in popular methods such as Mummer4. When you run this software on any real data, what you will see is that it allows you to compare large genomes. So, for example, you can take genome 1, genome 2 that are long, and what it can do is it can solve these maximal unique matches. It will further cluster them and do this dynamic programming recursion to tell you how these genomes match with each other. So, for example, it will show you the regions where these genomes show homology. It will also reveal the structural variation and rearrangements between these genomes. So, for example, you can see in this example there are some structural changes that are happened between genome A to genome B. So, similarly, there is another structural rearrangement that is being shown in genome A versus genome B comparison. So, such methods can enable fast comparison between large genome sequences, and this is where you can see maximal unique matches being useful. Now, so far from an algorithm perspective, we have only looked at how do we compute exact matches efficiently. In the next lecture, we are going to look at how do we cluster these exact matches, because observe that when we are computing these exact matches, there can be many matches that can also occur by chance. So, for example, maybe by chance we see an exact match of length 5 from just by random, but with clustering techniques we can find good clusters of those matches, so that we know that using those matches will give us good alignments also. So, in the next lecture we will look at clustering techniques which will allow us to locate a good cluster of these matches, so that we can ignore the matches that are maybe happening by chance, or they won't give us good alignments. So, we will look for formulations and we will look for algorithms that will allow us to locate good cluster of exact matches. And once we have good cluster of exact matches, then it is easy to do dynamic programming only along those cluster of matches, so that we do not waste time doing dynamic programming recursion in those matches which are just occurring by chance. So, see you in the next lecture. Thank you.